Hello everybody. In this video we're gonna talk about the steps that we follow to design a shell and tube heat exchanger. So this is gonna be a brief review of the steps. I'm not gonna go into details. I just want the audiences to be aware of the steps if they are not aware of it before. So that we can appreciate what the software will do. We will use the software to make a complete design of the heat exchanger with all the details of the design. And this is gonna be like a click of a mouse when we do it using Aspen Plus. And I want the people to know how impressive this is, that the software can do something that you would do in 2 or 3 hours. The software can do this in a couple of seconds. So this is very impressive. So let's go ahead and start with the information that we know about the heat exchanger, or about the streams that we want to exchange heat between in the beginning. So we know the hot fluid and the cold fluid, what they are. We know the flow rate of one of them. Usually, this is in general the givens that we have. The We know the inlet temperatures and the outlet temperatures of both. We know the pressures, the allowable pressure drop, and the allowable fouling factor. So these are the information that we know, and we want to get all the details about the heat exchanger that will achieve this heat transfer between the two fluids. So the first step is to find the flow rate of the second fluid, either this or this, whatever the one that we don't have. And so we can do like a general heat balance on the heat exchanger. We can say that the duty of the heat exchanger is the heat gained by the cold fluid, and which is, oh, this should be, I'm sorry, this should be hot. I'm sorry, this is a mistake. So this is just to differentiate between the cold and hot fluid. So this is the heat gained by the hot fluid, by the cold fluid, which is the heat lost by the hot fluid. And this is the UA delta T mean, is the overall heat transfer coefficient multiplied by the area and the delta T mean. We can from substituting in this equation, we can get the mass transfer the mass flow rate, which is the missing flow rate, and we can get the Q, the duty that we want to achieve. And we still have some information here that are not known, and these are the information that are related to the design, actually. And we will see that in details. So regarding the U design, we talked in the previous video that there are tables like this where you can tell what is the range of the values of the U design based on the two fluids, and from the table you can pick a value based on the two fluids. So still we don't know these two parameters, the A and the delta T mean. Let's talk about the delta T mean first. The delta T mean is, if we remember, when we talked about the counter current flow in the previous video, we said that the driving force is not constant. So we have delta T here different from the delta T here, different from the delta T inside the heat exchanger itself. So we use a value of the delta T, which is the delta T mean, or the logarithmic mean temperature difference, to be representative of the to the overall heat transfer inside the overall driving force inside the heat exchanger. It must be multiplied by correction factor, and this correction factor represents the deviation from the actual counter current. If we remember, if we take a look at the shell and tube heat exchanger, we said that because of the baffles and the direction of flow and all these things, we don't have pure counter current flow. So it's here kind of more like a cross flow, and in this case it's cross and counter current. So you cannot tell that this is a pure counter current or a pure cross flow. So we have this correction factor just to take into account that this is not the pure case. To get the value of the correction factor, we calculate it based on the values of R and S, which is the heat capacity ratio, which is the fall divided by the rise, the increase in the reduction in temperature of hot fluid divided by the increase in temperature of the cold fluid. and the S, which is the heating effectiveness, which is the rise, the increase in the temperature of the cold fluid, divided by the maximum rise that could be achieved, which is a very theoretical case when the exit temperature of the cold fluid is the inlet temperature of the hot fluid. So this is the rise divided by the maximum rise. And from these two values, we can get the correction factor from the charts. So the x-axis here is the S, which is it's S, and in this reference it was called P, but it's S actually. You can find S and R, and from the S and R you can find the value of the correction factor. Usually the correction factor shouldn't be less than 95% or 0.95. I think this is 0.95. This is what I remember. So if you go to the first chart, which is the one shell pass, you can calculate the value of FT. If FT is suitable, then we now know the value of FT, and we know now that we are using one shell pass. If it's not suitable, we go for two shell passes and then see if it works, and if the value of FT is suitable, then we have two shell passes and we know the value of FT, and so on. So we have the charts, we can find the value of FT, and then now we know FT, we know the LMTD, and we know the U design, so we can calculate the area that's required to achieve the heat transfer in in uh, in this case. So from the area, we know that it is the area of the tubes. So it's an area of one tube multiplied by the number of tubes. So this is the number of tubes, and this is the area of one tube, which is the perimeter multiplied by the length, the outer area of the tube. In this case, you'll find that, or in general, you'll find that there are some values that we will assume, like the diameter of the tube and the length of the tube. And there are some standard values, so we usually go for 1 inch for the diameter, or 3/4, whatever. I usually start with 1 inch, and for the length we have standards of 8, 12, 16, 20 feet. So whatever the value that you want to start with, you can go ahead and pick. And based on the values of the D and the L and the area, of course, you can calculate the number of tubes that we need. But actually, the number of tubes is standard. There are standard values for the number of tubes, so you cannot just pick the number that you calculated and go with it. So you would find tables like these. In these tables, let's say I'm using this is for square pitch, and we are using 1 inch outside diameter. And I'm going for two shell passes, for instance. I calculated the number of tubes and found it to be 130 tubes. So I go for two passes here in this part of the table of the 1 inch outside diameter of the tubes. And this is the column of two passes. I found it to be 130, so I picked the greater. So I have to pick from 112 and 132. So I picked the larger value, which is 132. So this by doing this, I know that this is a piece of information that I found, which is the actual number of tubes, and I find that this is the outside diameter, the inside diameter of shell. So I found another information. So I picked two information, the inside diameter of the shell and the number of tubes, and now I can calculate the actual number of tubes. I can calculate the actual area, and from the area I can update the value of the U design, and it should be within the range that I was choosing from in the very beginning. Now I should now be good. I have almost all the information that I need to do the calculation or to design the heat exchanger. Of course, there are some values that will be assumed, like the buffalo spacing. So this is something that you can assume, and there are standard values as well that you can pick from. But I now need to confirm that the design that I chose is suitable from the fouling point of view and from the pressure drop point of view. So I need to calculate the fouling factor and make sure that it is suitable compared to the allowable value that I have in the very beginning. So to calculate the fouling factor, which is the RD, I have to calculate the U clean, and if you remember, I need to go back here. the 1 over UA, which is the U clean, which is not taking into account the fouling, is equal to 1 over HI AI plus 1 over H out A out. So it's function of the heat transfer coefficient in the tubes and in the shell. And to calculate the heat transfer coefficient, it's kind of heat transfer thing or convection heat transfer thing. The heat transfer coefficient is function of Reynolds number and Prandtl number. So we calculate Nusselt number, and we from the relation between Nusselt number, Reynolds and Prandtl number, we can calculate the Nusselt number, and from Nusselt number we can calculate the heat transfer coefficient. So this is being done for the two cases. And this is the painful part of this, that this u 1 over u clean is a very tough, it's not tough, but it requires a lot of calculations. So you have to calculate the velocities, get all the physical properties of the two fluids at the operating temperatures. You have to calculate the mass flow rate and the velocity. We said the velocity, and you need to calculate the Reynolds number. You need to calculate the Prandtl number. You need to calculate the Nusselt number from the relation between both of them, and from all these you can calculate the heat transfer coefficient in the tubes. You repeat all these steps for the shell side. So you calculate this for both of them. And from this, you can calculate the 1 over U clean, and from the U clean and U design, you can calculate the RD. It's totally possible that after doing all these steps to find that the RD is not suitable, so you need to change something in the values that you assumed in the beginning and redo all the calculations. It's totally possible, and it happens a lot actually. And if any one of you have done the manual design of heat exchanger before, you'd understand what I mean. So this is the first thing that you want to check about, or to check. The second is to check on the pressure drop, and the pressure drop in tubes and in the shell side. So you calculate it twice as well. And here you calculate the pressure drop based on two values, or it's the summation of two values. The pressure drop due to the friction losses or the viscous losses, which is what we do in the fluid mechanics in Bernoulli equation. You calculate the F dash, which is the friction factor. So this is the friction factor or the term of the viscous losses. Of course, it's kind of complex because it's an empirical formula. It's taking into account the equivalent diameter, the specific gravity, the viscosity, the mass velocity, the length of the tube. It's kind of taking into account everything. And here you take into account the losses due to the change in direction. So you have and the sudden expansions and contractions, and this is what happens, or what's taken into account in this term. Again, you can calculate the pressure drops and find that the pressure drop is not suitable, so you have to do some changes. And this is what we do. If the RD calculated is smaller than the RD allowable, then you have to either decrease the U design by increasing the inside diameter of shell, or increase the U clean by increasing the number of passes or decreasing the baffle spacing. And of course, you have to keep in mind that each parameter that's going to be changed will affect the whole design. So it's gonna affect the heat transfer coefficient in the tubes, and this will have an effect on the pressure drop. So if you increase the passes, then it's gonna increase the heat transfer coefficient, and it's increasing the pressure drop a lot. This is to the power of 3. It's a very big effect. And again, for the baffle spacing, you are increasing the heat transfer coefficient in the shell, and again, it's increasing the pressure drop in the shell. So this is kind of the main guidelines in the design of the heat exchanger. This is the design based on or suggested by Kern textbook, which is the process heat transfer. And it's kind of one of the most famous design procedures for the heat exchanger. Now let's go to Aspen Plus and see how we will do or how we will deal with the heat exchangers. In Aspen Plus, there are two modes of working with heat exchangers. There is the shortcut mode, and there is the rigorous mode. The shortcut mode is kind of, as the name implies, it's a shortcut. It's a simple calculations. Uh, it doesn't take into account all the details of the design, like the number of shell passes, number of tube passes, the spaces of the baffles, the pitch, the inside diameter of tubes, and all these information are not taken into account. It just does energy balance on the heat exchanger so that you know that the heat lost from this side is gained by this side, and that's all. The details that we're just discussing in these videos are gonna be in this video are gonna be available in the rigorous mode. So in this mode, you can choose either to provide the desired heat transfer that you want to achieve, and then the software will provide you with the design that will achieve this heat transfer. And in the rating mode, it's the opposite. You have the inputs from one side, and you have the design, and you want to check how this design will operate, and this will calculate for you the exit temperature of the other side, so that you know that this is suitable or not. So these are the two modes in the rigorous mode, and this is the shortcut mode, and these are the two types of calculations in the rigorous mode. And this is what we're gonna do in the next videos, inshallah. So the next videos we will do, we'll solve this problem once by the shortcut mode, and then we will shift to the rigorous mode and see what we will get out of it. So we'll see you in the next video, inshallah. Goodbye.